All right, hey y'all. Hi, I'm Thelonious Cooper. I'm a junior at MIT, and I'm studying and researching under Cyravella of the Earth Signals and Systems Group. We'll be presenting a stochastic compound failure model for testing the resilience of fixed-wing drones. So we'll start with some motivations, applications, and algorithms with some long-term thinking, the algorithm that we implemented and evaluated, and then we'll talk about flight testing. So I'll hand it off to Sai.
Okay, so we're going to do a tag team. I'm Sai Rovella. I direct the Earth Signals and Systems group, and Theo's been working in our group. So one of the things I want to do is to set up a bit of motivation. We are somewhat both theoretical as well as applied group. Theoretical meaning we build control algorithms, and applied meaning we fly out there. On the top left in a sort of not so clear picture are two axes. The x-axis is the horizontal scale in meters, and the y-axis is in time. And the kinds of things we're interested in are small-scale turbulence, cumulus convection, volcanoes, hurricanes, cyclones. We care about all of these things, and what we care about is understanding how they develop, how they grow, how they explode, and characterizing them. The traditional way of doing this has been to use large, aircraft, and then we started with all sort of DoD giveaways. Expensive aircraft that we couldn't afford. We're small academics, we don't like to take any of these aircraft because they crash just as badly. And when they do, the price we have to pay is a lot more than we would like to. So we've been looking at small hobby aircraft like many people have been. And we started doing this sometime in 2013. And we finding that there's a number of issues with these, obviously, that we've been trying to address. So the kinds of things that we build are autonomous observing systems, and we study adaptive mechanisms to sample the environment. Here, for example, you see an aircraft that's buried behind the text over the Popocatépetl volcano, where we're taking measurements. We also fly over smokestacks, plumes, whatever it is. We just basically try to study the environment. One of the things we like to do is, the classic thing you do is you fly a lawnmower in the air. So the plane flies whatever pattern it does and takes measurements. But it's much more interesting when you can fly adaptively. If you can figure out that instead of just spending all that energy flying everywhere, if you could target where to sample, when to sample, how to sample, using a feedback loop between a prediction of what you think the environment's doing and a correction based on your measurements, it gets much more interesting. So that's the kind of thing we do. So this being a developers conference, I want to bring you down to the level of flight testing and to the level of coding that we do. So here's this typical environment, lots of crashes. And because we fly in volcanoes, we face a different set of challenges. Our challenges are not, of course, they're comp failures. If you fly in a volcano, you'll probably get electric field, you'll probably get water vapor, you'll probably get other things that you lose communication. But more importantly, it plays real havoc on the aircraft itself. We fly foamies, so this is not an easy thing to worry about, to try in a volcano. And more importantly, things like actuators fail all the time. Actuators get stuck all the time in these environments. All sorts of things go wrong beyond what you traditionally think of, like communication failures or maybe poor state estimation. There's much more going on the control side that can go wrong. So here, this is us flying in Mexico. Here's an example of a flight test that can go wrong. There's just a bit of audio, so we'll just watch. So everything's going well, the plane's doing well. Something happens. You know what this looks like? It's a spin. It goes down and down. The autopilot, in this case, we're trying to figure out how to bring it back using the autopilot. It works. It does. Somebody says, hey, turn it on. And they do, and eventually it tries to recover. But the loading is so high, it goes unstable, the wing breaks off, and down it goes into the ground. And a few seconds later, you're left with the pieces. Good news is it's foam. You put it in water, you stick it back together, it flies again in a little bit of time. But this is the kind of environment we often operate in, and it turns out to be quite a bit of disaster, and we're lucky. So this ended up in the trees, things didn't go bad. We could go back to the room, hotel, come back the next day, fly again. Okay, so what's the short of this story? The short of this story is that there are different kinds of failures. Sometimes people put mismatched wings. One wing has Kevlar on it, as you see on the top, the other doesn't. Sometimes they do silly things. Sometimes parts fail. Sometimes actuators get stuck. And these failures that happen in the field are not one-off things. They're incipient things that compound and cascade very quickly, partly because there's confusion between what the operator thinks is happening and what's actually happening, and partly because the underlying root cause is something more than just a simple superficial failure of one part. And so this is the type of regime we want to test. We don't want to test like you might get in an ACC conference or someplace where you go and you step the actuator and you see that your autopilot is really robust to it. We want to test some more real world scenario of cascading compound failures. Okay, so the first thing we did was we said, let's try adaptive control. What's the idea behind adaptive control? If there's a sudden change in flight configuration, we should be able to retune the controller gains on the fly so that the airplane adapts to it. And this should be great, for example, if you have a stuck aileron or a stuck rudder or something like that, we should be able to work, and this could get out of a situation. So we took the stock PX4 code, and we modified it with adaptive control, mostly to retune the attitude controller. So we haven't worked on other things yet, but we started with that and say, let's see the attitude control. I'm going to give you only one slide of math. That's a bit dense. So what's the idea? Standard control is based on PID control, so that's what you're familiar to, and there are gains on those. They might be feed-forward terms, but generally speaking, it's based on PID control. What if you could retrospectively look at the performance of your controller and adjust the gains in a way that the error retrospectively was minimized? This is of data you've already gathered as the flight's in progress. And then you use the adaptation of those control gains going forward. This is set up where there's a cost function that is a recursive least squares formulation that allows you to constantly update your gains. It's very easy to implement. We implemented it on the PixHawk environment. And I'm going to skip over these slides. You can go over them anytime you like, but the formulation is so simple, it looks like an RLS algorithm. It looks like something you might do for Kalman filtering, for example. It's just a set of parameters that you apply to the gains, and these parameters are constantly being updated over time based on the retrospective errors you've seen and the retrospective control inputs you applied and the retrospective and the current gains that you used. So we said, okay, now we're going to try this autopilot, and if everything works, this change we made should be so superior that we should have a better environment. To do that, we needed to produce a testing environment. So we went back to the field and we put together, so this is all just a picture of showing our little testing environment. The implementation of this, Theo will now talk about, and I'm just going to turn it over to him.
Sure, thank you. So I'm going to talk about the methodology of our evaluation scheme, the implementation, and the results we saw. So starting with the architecture, the system architecture, what we wanted to do is we wanted to test what these incipient failures look like. And so what we decided to do is we built a Markov model based on our subjective experience of how failures seem to cascade in the real world. And we tried to inject failures into the actuators at the I/O processor level in order to simulate those processors failing or the actuators failing in this scenario. But unfortunately, when we tried to implement it on the I/O coprocessor of the PixHawk, we couldn't meet the timing constraints and we got into all sorts of weird bugs. So instead, we moved to the FMU. And at the time, the failure module had not implemented actuator or motor failures. It now has, but regardless, we essentially spoofed the actuator controls DDS topic. We created a new instance of it where we then listened on the original one and then republished a faulty version of the actuator control signal, which gets sent to the mixer. So there's several different failure states. We have things like no failure, which is what you'd expect, and then we have each of the ailerons being jammed, the elevator, the rudder, the throttle, But what's interesting here is that these failures can compound on each other, and they form a Markov chain of failure states, where they can remain in the same state every second we update them. They can go back to the ground state where nothing's failing, or they can compound on each other and introduce a new failure.
So, may I?
Yeah.
So it's important to note here that we don't come up to a state where the aircraft is not flyable. You can imagine failing everything, and that's not something we do. So there are some which are marked not applicable. These are states that we think are fundamentally dangerous, like you're gumming up the elevators and you're gumming up the rudder and you're gumming up, basically all you have is a throttle left, for example. So, but this Markov chain has a transition probability that triggers every second, right? Every second it decides what to do, and it can transition to these. These have been based on experience, but in practice, we think that if we had access to a lot of flight logs, for example, and we could run a failure detection algorithm on those flight logs, we could learn what this transition matrices could be from them, and then we could replicate realistic failure behavior in the future. But for now, we've hand-coded these transition probabilities. They're like a third, a third, a third.
Yeah.
Something like that.
It's some weird parameterized thing. But
And so there's always one extra failure. You start with, say, the top one says there's no failure. The top one says it's no failure, and then the aileron left could gum up. And from there, the transition could be to aileron, the elevator gumming up or something else gumming up. But anytime you go from one state to the other, the aircraft is still flyable. In other words, if you were a human and you were trying to bring the aircraft back down, you could do it. And so that's the testing regime that we built. This for us was much more realistic, and it revealed a lot about the control law that I previously mentioned. And the previous control law that I mentioned is actually quite a robust control law. The retrospective cost adaptive control is so easy to implement, and it's so simple to implement on low-powered processors. And it had shown great performance, like on a quad rotor that we had previously done. So we were very thrilled to try out that kind of, and it could be used for all sorts of things like auto tuner, system identification, all sorts of things. But here we're looking at it specifically in the context of adaptive control.
Yeah, and so now I'll talk about some of the technical challenges that I faced in the implementation of this failure process. So the first one was that we tried implementing this on the I/O coprocessor, but the way that the I/O coprocessor operates, it essentially takes a bunch of data over serial, and then it just blind writes that into a memory mapped I/O scheme that is sent to the servos. And if you miss that timing by even a little bit, the entire thing breaks. So we found that the I/O coprocessor wasn't powerful enough to be updating these transition probabilities even every second. So then we moved to the FMU, and we decided to implement this in the PX4 module. And so we had to create new messages that trigger this new listening on the spoofed signal that we can then implement as this failure model. So one problem with this is when you start it, you need to somehow tell the mixer module to listen to this faulty signal and not listen to the signal it was originally listening to. So that required a new vehicle command implementation. And then the other problem is when you stop it, you need to tell the mixer to not listen to the faulty signal and listen to the original signal. The problem with this is that as you are scheduling the process and you instantiate a teardown of the process, you can deallocate the memory in the DDS space for the topic before the mixer understands that it's actually faulty. So what happens is you run into a race condition where the FMU starts reading garbage deallocated data, and you get all sorts of really mysterious bugs, and the simulator crashes, and it's very bad. But what we realized is that we can essentially have a cease command that triggers a pass-through or that tears down the process before we actually immediately tell it to stop allocating that process more cycles. So we ran this in simulation, and we gave it a flight path that is a Hilbert curve of various, or pseudo-Hilbert curve with various orders, and this basically just tests a variety of turning frequencies. So we want it to perform well when we're mostly on straights, but then also when we're turning constantly.
So I mean, so usually when you fly, if you're a pilot, you might take a test that says, okay, let's fly figure eights, turns around a circle. There's all sorts of standard flying skills you're supposed to have. But for us, the testing had to fill a certain area with a certain density of turning, because that's a good way to test how you might perform. And you can look at each one of these. These are like fractal diagrams, they feel like, but they're Hilbert curves which have different turning radii. And you can specify this quite easily. You write this computer code, and it'll generate a flight path, a random flight path with a certain density. And it will stress test, really, it'll stress test every degree of freedom you want to stress test. You want to stress test pitch up, pitch down, rolls, you want to stress test whatever it is, you can even stress test throttle up, throttle down. All of these can be completely automatically generated. But this flight path is meant to cover a whole range of actuations that you can do. Here, what you're seeing on the top left is the failure simulated by the PX4, and it's not perfect. If it were perfect, it would be just straight lines, but this is the flight path flown in simulation by the PX4. Maybe you want to explain this diagram in more detail.
Yeah, sure. So we gave it the Hilbert path as the flight curve, and then we simulated what happens when it actually flies this with these induced failures, and we see that it has little instances where part of it, if an aileron fails, it might do a loop for a second before trying to recover. And then we did this for multiple autopilots. So for the stock PX4, for the retrospective cost adaptive control, and for a mix of the two with a mixing parameter, alpha equal to 0.5. And you can see that the mix was actually significantly worse than either of them, which was interesting.
So just to elaborate on the concept of mixing, there are two control laws. One is the stock PX4 control law, and the other is the adaptive control law. And these are both being mixed with some alpha, some fraction. And the reason for this is if we just use the adaptive control law, it has horrible performance because you need to have a well set up controller initially from which to adapt. You can't just adapt from a random initial state. So we experimented with going all the way down. Alpha 0, for example, would mean just the stock, and alpha 1 would mean just using the retrospective cost adaptive control law. And so depending on this fraction, we get a different answer. And so we would think that, when we have basically a fully adaptive controller after we've flown the aircraft for a while, because the gains the gain tuning has stabilized a little bit, that it would lead to really good flight. But maybe you want to explain which one really performs poorly.
Yeah, so we can see that the mix alpha equals 0.5 performed the worst, and I should mention how we're actually evaluating the performance of this. It's with an algorithm called dynamic time warping, where essentially we're measuring the distance between the curves under an approximation of the Wasserstein metric, which is essentially the Earth mover's distance. If I have some curve, how much do I have to move it in order to make it another curve? And so this kind of measures the resilience in the aggregate to these perturbations, so that we can see how each of them managed to stay on course or didn't. And so then our results were quite surprising, where we saw that PID actually outperformed RCAC under our evaluation scheme, likely due to a bias variance trade-off. So here on the y-axis is the distance between the curves and the target curve, and in meters, what are basically meters. And then we see the stock PX4 without any failure simulation has very low variance. That makes sense. Same with the RCAC at 0.5 with no failure simulation. Same with the RCAC alpha equals 1 at no variation. And then we see that when we introduce these failures and we simulate it many, many times, we get some distribution over this metric, or approximation of a metric. And the variance of the RCAC controller was actually higher, and it performed a mean slightly worse than the PID controller, likely because you can think of it as perhaps having overfit its model of the tuning, where the total error is some function of both how far away it is from the ideal tuning and how quickly or how much the tuning varies. But it was quite surprising to see that the PID outperforms this control law.
Yeah, and if you think about the kind of failures that are being generated, it's flying, and then the left elevator would get, aileron would get stuck for a few seconds, and then the right aileron would get stuck for a few seconds. Maybe the rudder gets stuck, maybe something else happens. So these things start compounding, and they get stuck for longer and longer times. And you would think that the adaptive controller would simply keep adjusting the gains in a way that will compensate. But what you're seeing here is a very interesting result in that the stock PID controller, and then by stock we mean we couldn't do any extensive tuning either.
Quite literally what comes out of the box.
It was very, very resilient to these failures. And if we go to Alpha 1, which is fully the retrospective cost controller, it offers no particular benefit. And the worst thing to do is to take half and half, which is actually neither here nor there, because the performance there shoots through the roof. When it's a perfect world, things look good, but as soon as you inject these disturbances, one can't compensate for the other well, because the control inputs feedback and it doesn't seem to work. So one conclusion we draw from this is that when we're thinking about adaptive control, if there is just a one-off change, which you'll find numerous publications on, I stuck an elevator, look at how good my curve looks. So when there is just one-off change at a very low frequency or at a long time scale, enough for the controller to readjust, I think life is very good. You can use adaptive control all you like. But in the case where lots of things are going wrong, this is not a feasible, it doesn't appear that this is a feasible path. So we want to think about that a little bit more. But our testing was able to reveal this, and we think that this testing regime could actually help other people, because if you are interested not just in actuator failures, but you want to incorporate COM failures, you can incorporate other things, processor failures, we can easily do that in this setup.
It's of note also that RCAC slightly outperformed PID when there were no failures injected, which is to be expected from this controller. So some of our conclusions are that adaptive control is a topic of great interest, because as we try to soar to greater and greater heights with cheaper and cheaper UAVs, it's important to be able to handle anything that comes at us. And then these kind of ensemble outvaluations, where it's not just a one-off perturbation, but actually many perturbations over many simulations, provide deeper insight into the performance of these control laws than the typical step response or impulse response of the controller. And further, it's unclear, as we stated in our results, whether these modern adaptive control laws, which have gotten lots of fanfare from the controls community, are actually superior in these applications. It seems that it's actually better to have a perpetually mediocre controller over a very skilled controller that then has to completely reevaluate itself as soon as anything changes.
I'd add a slight caveat to that. I mean, we think about this as a bias versus variance issue, and this is also true of previous talks on, like, for example, the deep learning setup. So if you have something that is very good at adapting and sticking to a new situation, it also has a problem when the situations are really broadly changing. In that sense, it's better to be like the the mutt, the sort of generalist, which kind of doesn't do well in all of them, but does a reasonable job in all those scenarios, versus an adaptive controller that tries to do well everywhere and can't, as the number of issues that go wrong compounds. And so this is true even when you do learning. So for example, if you're trying to do state estimation using learning, if you train it on a certain regime, you'll get really good performance. But now, if the regime changes, you could potentially retrain on the fly, incrementally, online, in the air, and get good performance. But now when you start getting many different scenarios that you're in, perhaps very complex maneuvers, you have a problem. This is a trade-off between bias and variance you cannot escape. So I think that we should be careful in going to more and more nonlinear, more and more sort of adaptive schemes. That's a lesson that I would say we really draw from this simple exercise.
And further, the Earth Signals and Systems Group is looking for collaboration to develop the next generation of controllers which hopefully can handle this sort of thing, usually through coactive learning. And we are interested in the community's flight tests and flight log to see if we could glean the actual transition probabilities for the failure model from real data. And lastly, we offer our support in developing this methodology and offer it for anyone to use in their development of new control laws. Yep, thank you.
Thank you.
Do folks have any questions? Yes?
More than a question, it's like a suggestion. All my life I have been building RC aircraft for fun. I think you could find, do you know what IMAC competition are?
I'm not familiar.
Well, IMAC competition are acrobatic competition to fix with airplanes, but they are airplanes designed to 3D fly. Like, I don't know if you know the airplane extra 200, like the Red Bull Race.
Oh yeah, okay, I've heard about it.
In that competition, pilot make very aggressive maneuvers close turns like a torque roll. I don't know if you have seen it.
Mm-hmm.
When they leave the plane in a single spot, hanging by the propeller, and they also do flying night. I don't. My English not very good, sorry. The night flight. It's a maneuver like they put the airplane 90 degrees and a speed almost like and in a speed like if the plane is going to reach stall, and they started to move crazy. That airplanes are very good built because there are people that make competition for that. And when that plane fail, some of these pilots have the ability to land without a wing, without an elevator, without a rudder. You could just simply search for one of these pilots in your area and tell them what you are doing. Tell them you want to put the PX4 between the servos and the receiver. Switch up, for example, a wing and see how the pilot reacts and try to learn how fixed wing aircraft can fly without the wing, without engine.
Yes.
It would be a great data source
Yeah.
for this.
Yeah, I have a couple of counter comments, perhaps. One is the acquisition of human level skill performance in some of these competitive flying is a slightly different topic, especially when we think about learning and online and nonlinear control. There's lots of interest in it. We have some thinking, but I want to slightly, so we will pursue that, and there's some interest. But I want to point out slightly different. NASA did a lot of experiments, and in their autopilot, so what happens is the plane is or spacecraft is perfectly flying on autopilot, then it comes close to the ground and things go bad, and it says your airplane to the pilot, and the pilot can't do anything about it. They're just other than crash it, because we have to ask ourselves, what is the regime under which this autopilot works? In the environments we live in volcanoes or inside hurricanes or up from the stratosphere, the purpose there is to be robust, not just robust to what's going wrong, but to be resilient. Like when a series of things goes wrong, it has to fly with what's left. That's a skill, that part of the skill, if humans are really good at it, we should learn from it. But from our experience, the skillfulness of a human's performance really is not, it's resilience to lots of things going wrong. It remains to be seen. But I'm going to investigate what you pointed out, and maybe there is something there to really get data from to emulate.
I'm pretty sure you will find very interesting info on how an aircraft survive in these scenarios if
Great.
that competition.
Sure.
Yeah, thank you. Any other questions?
Yeah. So were you testing an AI model? Controller? Is that
So it's not, I guess it's AI in the way that any algorithm is AI, but it's not like a deep learning kind of scenario.
Well, let me answer that question. So what's happening is, as your aircraft is flying, the controller is operating and it's producing control inputs. And you also got the state estimates all along as you've been flying. And you know what your goals were, so where you needed to go, what your demand was. So if you could go back and say, hey, if I could retune my PID gains, would I get a lower error from the things I've already observed in just the recent past? Could I get a lower gain? And if it's possible that you could reduce that error, then you've got a better gain setting. Now, why would that error grow in the first place? Well, something happened to the aircraft, like maybe a part failed, and now you get a sluggish servo. You can only fly on one end, and your rolls don't look as good. Those are, or things like that. And so, is it AI? It is, because it is having this data-driven component that is trying to learn from what the previous performance was, but it wouldn't be called AI in the community because it's just really doing regression, like recursive least squares. So it's of the same class of algorithms as a Kalman filter, which is being used for a state estimator. Very different than that, though, but it's of the same class of algorithms. So it's a kind of borderline thing to call it AI. But it is in the sense that it's using data, past performance data, to improve, but it isn't in the sense that it doesn't have fancier algorithms like decision trees or random forests or neural networks to do that regression problem.
Yes, thank you.
So my understanding of all this is that when you detect an error, then you adjust the PID parameters. This is correct.
Yeah.
Because what I think you should do instead is like if there is some failure occurs, because you just adjust the PID parameters and still try to follow the planned trajectory, that might not be a good idea, because when the aircraft is heading down, you might want to adjust the goal instead of maybe the control parameters to first
So 100% agree with you. In the holistic situation, you have to bring everything on the table. You might say these goals are not achievable. Let's try to go for something else. This path is not flyable. Let's go somewhere else. But that's the next level in the intelligence hierarchy. There is a level at which the autopilot says, can I adjust to what's going on? So we haven't stressed it in the way you are suggesting. We've stressed it in the Hilbert path stresses a lot of roll rates and rolls, but that's the normal regime. It's not the kind of level of failure where you have to abandon a goal, for example. It might be, but absolutely agree that that's something that should be considered at a different level. Yeah. And we could fold that into the control algorithm, but now the control algorithm gets to be very unwieldy because we're talking about low-level PID control. Well, on the top of this sits the trajectory controller. On top of the trajectory controller sits the finite state machine or whatever machine you have for transitioning through different states of the system. Then there's the goal planner. There's like all kinds of hierarchies of the system that have to go up and down. You can do the whole thing in one monolithic stack, but that'll become a very unwieldy code and really hard to kind of understand what it's doing. But if we have this hierarchical setup, which is standard in terms of hierarchical planning, we can do exactly what you're talking about.
Yeah, thank you all.
Okay, thank you.